The universe isn't fixed. It never was. But for most of human existence, that's precisely what we thought. Gaze up into the night sky. The stars don't appear to move. The constellations remain the same night after night, year after year. The moon moves smoothly. The planets stray a bit but always come back. To ancient eyes, it all seemed permanent, still, like a grand cosmic canvas suspended over the world. So we constructed our concept of the universe on that stillness. The Earth, we believed, had to be the center, solid and immobile. The rest, the sun, the stars, the heavens must be rotating around us. A perfect heavenly dance initiated by something divine but perpetually repetitive. For centuries, this perception held not because humans lacked imagination, but because it worked. It fit what the eyes could see. It explained the seasons. It explained eclipses and alignments. It provided us with comfort, a secure world under our feet, surrounded by orderly skies. Then there was a crack in that illusion. First, Copernicus dared to propose the Earth was not the center after all. Then, Galileo pointed a telescope at the heavens and observed moons revolving around Jupiter, evidence that nothing else revolved around us. Then Kepler arrived, who observed the orbits of planets and found that they didn't trace perfect circles, but ellipses driven by unseen forces, obeying strict mathematical laws. Slowly, slowly, the quiet was gone. Now we know the truth is much stranger than anyone ever dared to dream. Space isn't quiet and stationary. It's in motion all around. Not only planets and stars, but galaxies, clusters, and superclusters. Even the fabric of space itself is in motion, expanding in all directions. And yet we still manage to feel like we're standing in one place. The ground doesn't rock. The stars don't whiz past us. The universe is peaceful. But that peace is merely an illusion of scale, a mirage. For the reality is, even now, at this very moment, we're rotating on a planet, around a star, hurtling through a galaxy, all while being drawn by something we can't even see. The old image of an unmoving universe is no more. We've entered a tale of unperceived motion, and we're finally coming to grasp what that motion tells us. For centuries, the prevailing conception of the universe had positioned Earth at its absolute center, and that was what people believed. By day, they watched clouds pass overhead and the sun shining bright above. Nights, they watched the moon and stars spread out like a giant cosmic painting. All these objects in the sky seemed to move, and they thought they were at the center of everything. This belief was shared throughout the ancient world from Chinese cosmology. But it was in the Hellenic world that this conception not only became an accepted myth, it was formalized into a technical cosmological model. And the person who did that was Claudius Ptolemy. Ptolemy resided in Alexandria during the 2nd century CE during the peak of Roman Egypt. He was a scholar, a mathematician, and above all, an astronomer who sought to impose meaning on the skies, not just philosophically, but numerically. He inherited a generous legacy from Babylonian star catalogs, Egyptian astronomy, and Greek geometric modeling, but did something monumental with that knowledge. He compiled, systematized, and perfected it into a systematic model of the universe set out in a gigantic work called the Almagest. The work so powerful that it became the universe's authoritative guide for more than 1,000 years. In Ptolemy's universe, Earth hung in the very middle of things, motionless and still. Around it, in nested spheres, everything else moved. The moon, Mercury, Venus, the sun, Mars, Jupiter, Saturn, and lastly the sphere of fixed stars. Beyond that, nothing humans had any knowledge of. The whole cosmos was a gigantic set of nested spheres, precisely arranged with Earth as the center of all celestial movement. Every celestial body was contained in a clear crystalline shell that rotated freely around us. The stars were attached to the outermost shell that rotated once a day, providing us with night and day. This was not merely a guess. Ptolemy used observations to make his model mathematically viable. He assumed the heavens had to move in perfect circles because the circle was the most perfect form in Greek philosophy. But that presented a dilemma. As people followed the planets across years, particularly Mars, Jupiter, and Saturn, they observed odd patterns. Occasionally, a planet would slow down, stop, and even reverse itself in the sky before continuing its forward journey. This retrograde motion didn't make sense if all the worlds orbited in simple circles around Earth. So to correct that, Ptolemy added epicycles. These were little circular orbits that each world made while that whole little circle orbited Earth on a bigger circle known as the deferent. So a planet didn't simply orbit Earth. It orbited a point which itself was orbiting Earth. This orbital motion could duplicate the backward steps in the sky. But even that wasn't enough. The arithmetic wasn't quite matching what astronomers saw. So Ptolemy added yet another adjustment, the equant. That was an imaginary position slightly off-center of Earth. He said that if you took the motion of the planet from this equant position, the motion looked uniform, not from the true center, but from this offset location. The model had been perfected for centuries, honed and revered. It had influenced calendars, clocks, astrology, and religious beliefs. It had served empires and guided scholars. It had explained the skies for over 1,000 years, but no amount of complexity could hide the truth forever. Observers were beginning to ask hard questions. A few began looking for a simpler explanation. And one name stood out, a name whose revolution still echoes to this day. It all began quietly in 1543 with the publication of a book that would shake the origins of astronomy. Its title was The Revolution Orbium Coelestium, on the revolutions of the celestial spheres. And its writer wasn't some great scientist or philosophers. He was a priest. His name was Nicholas Copernicus. That might seem strange nowadays, but at the time it was appropriate. The church was the hub of intellectual life in Europe. If you wished to study mathematics, astronomy, or philosophy, the church was where you did it. Monasteries and cathedral schools were their libraries and laboratories. Born in modern-day Poland, Copernicus learned law and medicine, experimented with economics, and learned Greek and Latin. But his true love was the sky, and for years he had been making secret collections of observations, crunching calculations and scribbling out an idea that had been developing in his head, one that contradicted all he had ever been taught. His concept questioned the whole system that people thought, so he kept it largely to himself. For many decades he held back, aware of the dangers, not only scientific ridicule but religious and political repercussions as well. At the end of his life, he finally published that concept unwillingly. In it, he described a model of the universe with the sun, rather than the Earth, at its center. The Earth, he asserted, was a planet like Mars and Jupiter, and it revolved around the sun once yearly. But he didn't leave it there. From what he had observed, Copernicus hypothesized 3 different motions of Earth. First, Earth spins on its axis every 24 hours. That daily spin is what causes the stars to seem to rise and set across the sky. Second, Earth travels around the sun once every year. That trip around the sun accounts for the shifting positions of the planets and the changing seasons. And third, Earth precesses or wobbles, moving in a tiny circle as it travels on its orbit, a motion that we now attribute to the tilt of Earth's axis and the process of precession. These concepts were not mere conjecture. Copernicus spent decades working on intricate geometric models and astronomical tables. He employed trigonometry to determine the relative distances of the planets from the sun. He arranged the planets according to how quickly they seemed to move across the sky. The nearer a planet was to the sun, the quicker it moved. That fitted very well with what he observed. But although Copernicus' model made sense in a conceptual kind of way, it did not increase accuracy. That was because he moved in ideal circles just as Ptolemy did. And that made his forecasts no better than the previous scheme, and in some instances, worse. And then the telescope arrived. It was not discovered by a scientist. In fact, it began as a Dutch fad, just a couple of lenses pushed together by spectacle makers. But when word of this bizarre instrument reached Italy, one man envisioned something beyond novelty: Galileo Galilei. He did not invent the telescope, but he made it into a tool of science. In 6009, Galileo aimed it at the heavens, and what he observed would shake the old regime. He gazed first at the moon in the eyepiece. It was not the ideal smooth divine sphere that the ancients had thought. It had mountains, craters, shadows. It resembled Earth very much. He then gazed at Jupiter. and there dancing across the globe were 4 tiny points of light. Night upon night he followed them and they moved position, but were always close to Jupiter. They were moons orbiting something besides Earth. It was gigantic discovery because the geocentric model said that everything must orbit Earth. But here was Jupiter hijacking that spotlight with its own orbiting system. Then he looked at Venus, and that was it. Venus cycled through phases, just like the Moon. At times it seemed full, sometimes it was but a crescent, and that only made sense if Venus orbited the Sun, not the Earth. If it orbited Earth, you'd ever only see it in one phase. But if it orbited the Sun and we were, then the geometry worked. That little glowing spot confirmed Copernicus was on the right track. But Galileo wasn't the man who eventually cracked the maths. That was left to someone else. Someone who didn't even have faith in Copernicus initially. Johannes Kepler was a German astronomer and mathematician, extremely religious, extremely inquiring, and achingly accurate. He caught the break of a lifetime when he became assistant to Tycho Brahe, the last great naked-eye astronomer. Brahe was a Danish nobleman who spent decades collecting the most accurate measurements of planetary motion ever made, all without a telescope. He built giant instruments in his observatory on an island and charted the positions of planets with mind-numbing precision. Now Brahe didn't buy into the Copernican model. He had his own hybrid theory where planets orbited the Sun, but the Sun orbited Earth. He tried to split the difference, but when he died in 6001, he left all of his data to Kepler and Kepler dove in. He spent years trying to make the Copernican system match Brahe's data, especially Mars. And Mars was tricky. It doesn't move in a nice simple circle. It speeds up and slows down, loops across the sky. It just wouldn't behave. For years, Kepler tried to force the data into circular orbits. That's what everyone thought. Circles were perfect, divine. Heaven had to orbit in circles. But Mars cared not for philosophy, so Kepler finally ceased to force the mathematics. He allowed the data to tell him what it was saying. And what it said revolutionized everything. Kepler found that planets don't travel in perfect circles at all. They travel in ellipses. That was his first law. All planets orbit around the Sun in elliptical paths, with the Sun at one center of the ellipse. This implies that the path of a planet is not a perfect circle, but more an oval shape. Kepler saw something else as well. Planets do not travel at constant speeds. They sweep through space more quickly when they are near the Sun and more slowly when they are far away. That's his second law. An imaginary line from a planet to the Sun sweeps over equal areas in equal periods of time. In other words, as a planet moves along its elliptical orbit, the area it sweeps out in, say, a month, is always the same, whether it's near the Sun or far. This explained the strange speeds of planets, especially Mars. And then came the third law, the one that stitched the entire system together, also known as the law of periods. Kepler determined that the square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of its orbit. That is, the farther away a planet is from the Sun, the more time it takes to make one trip around. And this correspondence is predictable. Coupled together, Galileo's telescope and Kepler's equations did something extraordinary. One provided individuals with the vision to envision a new universe. The other provided them with the mathematics to substantiate it. Copernicus had lit the fire. Galileo added fuel to the fire, and Kepler constructed the skeleton that eventually made it stand. Once the door was open, before long others passed through the door and moved further. The next generation advanced to the next questions. Why do planets orbit in the first place? What holds them back in orbit? Why don't they shoot off into space or crash into the Sun? That's when the legendary falling apple came into the picture. Newton named this unseen force gravity. He understood that the same force that caused apples to fall off trees also kept the Moon in orbit, had Earth orbiting the Sun, and dominated the dance of the planets. He expressed it as a law, universal gravitation. For him, any object that has mass attracts any other object, and the larger the mass, the larger the attraction. The more distant they are, the smaller the attraction. With Newton's law of universal gravitation, we knew that Earth moves around the Sun at some 107,000 km/h. That is close to 30 km/s. Mercury travels even faster at 47 km because it's nearer the Sun and has a greater gravitational pull. Mars, being further out, travels at a slower pace. It all works out. The nearer a planet is to the Sun, the quicker it must travel in order to orbit. Newton's calculations showed it to be so. He linked the movement of the heavens with the movement down here on Earth. For the very first time in history, we had a single everything. And poof, the universe's great cosmic puzzle of planetary movement, why they move, how fast they move was a puzzle no more. It was gravity. But there was more, something nobody anticipated. Because as scientists mapped the heavens with improved tools and more precise math, they saw another movement, a larger one, a deeper one. The Sun, the thing we believed was stationary, wasn't. It too moving. But where? After the Copernican revolution, the Sun took the Earth's place as the center of everything. No longer did the cosmos revolve around us. Now it was the Earth that moved, spinning on its axis and orbiting the Sun. This idea felt revolutionary. But once the paradigm shifted, the new model, the heliocentric one, began to settle. The Sun, which was once merely another thing in the sky, became our still point, the anchor of the universe, solid, unmoving. And for a couple of hundred years that notion held true. But that would soon change. Not with a physicist, not with a philosopher, but with a musician. William Herschel was born in Germany and immigrated to England as a composer. But he had an obsession, telescopes. He began constructing them in his free time, grinding mirrors and crafting optics superior to nearly anything else he had ever seen. And when he aimed those telescopes at the sky, he didn't merely gaze, he counted. Herschel became fascinated with pattern. If the sky was covered with stars, were they randomly scattered or was there a pattern? He determined to find out the hard way. He and his sister Caroline set out on a huge survey. He'd measure stars in thin slices of the sky a few degrees across and record how many he could see in each direction. Years went by, and these counts gave a pattern. He observed something peculiar. Some directions had many more stars than other directions, and the greatest density. It aligned with that thin band we know as the Milky Way. So he made a map based on star counts. He built what he believed was the form of the universe. And it was a flat, broad disk, like a grinding wheel with the Sun somewhere around the center. Today, we understand that he estimated the size incorrectly. He failed to include interstellar dust, which obscured many far-off stars from view. But for the late 1700s, that was remarkable. He had realized that the stars were not endless. They were contained within a structure, a system, and we were within it. He referred to it as the galactic system. But Herschel did not realize it was a galaxy in the modern understanding. He believed this system was the whole universe. He did not know that those blurry patches of light, those so-called nebulae, were other galaxies incomprehensibly far away. Nevertheless, what he did perceive was groundbreaking. He demonstrated that we weren't at the center of it all, not even remotely, and that flat form, it implied something. It indicated structure, movement, orientation. If the Milky Way were shaped, then we had a place. If we had a place, then perhaps we were moving too. That's when individuals began to ask an ulterior question. Where are we actually? And how do you even know what's moving and what's not? Because if everything is in motion, how do you know when something is standing still? That's when we reach a wall. Not a wall of data, but a wall of viewpoint. Because everything that we see from here from Earth. Our eyes, our telescopes, our equipment. They're all positioned on this spinning rock that's itself orbiting the Sun, which, as Herschel suspected, might be moving too. So, how can you tell what's really moving and what's not? That's where a frame of reference comes in. Let's try a simple thought experiment. Imagine you're sitting in a train. You're sipping your coffee, reading a book. Out the window, you see another train next to yours. For a moment, it looks like that train is sliding backward. But then, wait, are you moving or is it moving or are you both moving? Here's the thing. Without seeing the ground, you can't know for sure. That's the trap of your frame of reference. From inside the train, everything feels still. The coffee stays in the cup. The book lies peacefully in your lap. But to a person on the platform, you're swooshing past at 80 kilometers an hour. So who is correct? Well, indeed, both are, because motion is not absolute. It's relative. And when your sole window into the universe is from within that moving train on a rotating Earth in a star system that's moving as well, sorting out what's actually in motion is a puzzle, a mystery which one man went about solving quietly and patiently. Jacob's captain never thought of himself as a revolutionary. He was a quiet, cautious man who preferred numbers to noise. But what he did with the numbers changed our concept of the universe. Captain was born in the Netherlands around the middle of the 9th century. By this time, Herschel's star charts were already more than a century old. The notion that we were within a star system, the Milky Way of which we now speak, was accepted. But the shape, the movement, that was still a blur. Telescopes were improved, but astronomers did not simply require better instruments. They needed a change in approach. That is what Captain introduced. He began gathering data. Not only light, not just position, but proper motion. How stars move across the sky over time. These were small changes, frequently fractions of an arcsecond annually. But with the right math and sufficient time, they told a story. He collected observations from observatories all around the globe. The Cape in South Africa, Cordoba in Argentina, Sydney in Australia. Piece by piece, he built star catalogues, thousands upon thousands of them, recorded their brightness, recorded their position, observed them drift. And then something odd appeared. The stars were not drifting at random. They moved in patterns. Two broad streams, akin to cosmic currents, appeared to run across the sky. Initially, it seemed that the stars were two huge revolving swarms clumped together. But Captain pondered more. What if this had nothing to do with the stars? What if we were actually moving? Back to the train analogy. Think you're in the midst of a crowd, marching steadily through a crowded plaza. People appears to be passing around you in various directions. But perhaps it is the moving one, and everything else only seems to drift due to your frame of reference. Captain then took the leap. He did the math, and it all worked. The motion pattern of the stars only worked if the sun was moving and pulling us with it. This movement became referred to as the solar apex. To the captain's findings, the sun was moving toward a location in the constellation Hercules at around 20 km/h, not a hot dash, but a slow, quietly drifting across space. And with it, the sun lost its quiescence. But Captain did not let up. He wanted to get bigger. If we're traveling between the stars, then what is this cluster of stars? What is the form of the system we're within? Based on the motion and luminosity of stars, Captain started building what he thought was the actual form of our star system. He presumed stars were scattered evenly in space and that their luminosity diminished with space. On the basis of that, he designed a model. It resembled a flat disk-like object of around 40,000 light-years in diameter. And within this structure, the Captain universe, the sun was located close to the center. It was our initial serious effort to chart the Milky Way as a whole. Naturally, we now know Captain's universe was not large enough. He had no knowledge of interstellar dust, microscopic particles suspended in space between stars that scatter and absorb light, particularly in the direction of the galactic plane. This made distant stars appear dimmed and closer than they actually were. Thus, his model underestimates the size and shape of the galaxy. But for its era, it was revolutionary. And then came a breakthrough. Astronomers started questioning those dim, blurred spots in the sky, the so-called spiral nebulae. Some thought they belonged to our own Milky Way, but others intuited something more sensational, that these could be full star systems unto themselves. That's where Edwin Hubble comes into the picture. Working with the Hooker telescope on Mount Wilson, then the world's most powerful telescope on the planet, Hubble trained his sights on one of the brightest of those nebula Andromeda. In 1923, he saw something important within it, a type of star called a Cepheid variable. These stars vary and decrease in a familiar pattern, and due to Henrietta Swan-Leavitt's previous research, that pattern could be utilized to estimate how distant the star actually was. The result amazed him. Andromeda wasn't merely distant, it was way past the border of the Milky Way. So distant, in fact, that it couldn't possibly belong to our galaxy. This was a huge transition. For centuries we believed the Milky Way was the whole universe. But now it was only one galaxy among many, a lone island in an immense cosmic ocean. But here's the important part. By looking at these other galaxies, we started seeing our own in sharper focus. You can't view the Milky Way from the outside. We live inside it. It's like trying to map the shape of a forest from the base of a single tree. But with Andromeda and other galaxies, we finally had something to compare it to. We could look at galaxies from the outside and ask, does our galaxy have a spiral structure like that one? Does it have a central bulge, a flat disk, a halo of stars? Throughout the ensuing decades, astronomers employ this mirror analogy, contrasting outside galaxies to what we might see from inside the Milky Way. They charted clouds of gas, star clusters, and the spread of different stellar populations. They employed radio astronomy to peer through dust that obscured sight in visible light. Slowly, a new picture formed. One of them is a Dutch astronomer by the name of Jan Oort, who came closer to studying the motion of stars close to the Sun. He was not only curious about where the stars were, but how they moved. And what he noticed was peculiar. If the Milky Way were spinning as a solid wheel, all the stars must be moving at the same angular velocity, like the spokes in a bicycle wheel. But they weren't. Some stars were behind, some were ahead. It resembled a whirlpool rather than a wheel. Or calculated the figures and discovered the galaxy rotates, but not uniformly. It rotates faster towards the center, slower towards the outside. He developed the mathematics of this, and derived two constants that accounted for the way stars moved close to our location in the galaxy. These constants, now known as the Oort constants, provided the first detailed description of the differential rotation of the Milky Way. From that, he estimated our Sun is approximately 30,000 light-years from the center of the galaxy and traveling at a mind-boggling velocity more than 200 kilometers. That's so fast it would orbit the Earth 7 times in 1 minute. Traveling at that rate, the Sun takes approximately 225 million years to complete a single orbit center. That's 1 galactic year. And the Sun is not alone. All the stars you see in the sky are doing the same thing, revolving around the center of the galaxy like bees around a hive. We just don't notice it because we're all moving along together. But if that's true, what are we orbiting? To find out, astronomers needed better vision that could see more than visible light. So they looked to radio waves. Specifically, they began mapping out the faint natural radio signal given off by neutral hydrogen atoms. At a wavelength of 21 centimeters, this signal could pierce through the thick clouds of dust that made optical observations nearly impossible. By tracking this signal, astronomers began to map the spiral arms of the Milky Way from the inside. It was like attempting to paint a landscape of a forest while being within the forest. And now they had the technology to accomplish it. And then one of the largest strides forward was taken, the Very Long Baseline Array, or VBA. The VBA is not a telescope. It's an array of 10 radio antennas distributed over thousands of kilometers. Picture setting up 2 telescopes on opposite sides of the planet. Say one in Hawaii and one in the Virgin Islands. Now picture syncing them so nicely they behave like one huge dish the size of the entire continent. That's basically what the VBA does. It connects 10 radio telescopes spread out across the Western Hemisphere to become one super device that can look at things in the sky and resolve incredibly small motions. And by small, we're talking about changes so small they are measured in micro-arc seconds. That's like seeing a coin on the moon from planet Earth. They're using this system to monitor cosmic beacons known as masers. These aren't visible lasers with your eyes. They're radio pulses naturally produced by clouds of gas around newly born stars. These masses function like lighthouses in space, shining, dense, and ideal for monitoring. Because they are anchored to individual areas within our galaxy, they help us identify both position and velocity. In the course of 39 years of watching, astronomers observed these masers crawl across the sky. They observed their shift in 39 position, that's proper motion, and also how their light moved towards red or blue. That's radial velocity, whether it's approaching us or receding from us. Add those together, and you have a complete 3D image of motion. Not left and right, not merely forward and backward, but the entire dance of stars along the Milky Way. And what did the dance indicate? It indicated the stars revolving around the galactic center, but not in neat circles. Their motion is a spiral pattern distorted and stretched by the force of gravity and the geometry of the galaxy itself. Some arms are in the lead, others lag behind. Clusters sway, gas clouds shear under tidal forces. But there was more to it too, something peculiar at the center of it all. As these mesas and other stars were followed closer and closer to the galactic core, something became clear. Their velocity accelerated wildly. Objects orbiting close to the center were whizzing by at crazy speeds. But the kicker is this: there wasn't sufficient visible matter there to account for that sort of gravity. There were stars, yes, dust, gas, but not anywhere near enough to keep things together at those velocities. Something intangible was keeping the galaxy together. And all that movement, all that mathematics, all those accurate measurements, they all led to the same location: a dense, tight radio point close to the constellation Sagittarius. That point is called Sagittarius A. It doesn't appear like much unseen light, just a cloud of stars and dust, but in radio waves it glows. VLBA observations targeted it, and what they saw was an immobile object as compared to which everything else was revolving. It weighed more than 4 million times the Sun. Its diameter is less than the orbit of Mercury. The one thing in physics that matches those numbers, that small, that dense, that massive, is a black hole. A supermassive black hole. That's what holds the Milky Way together. It's there quietly at the center, hardly twitching, while all the stars, all the planets, all the gas clouds in the galaxy spin around it. And even so, we're not standing still because the stars aren't merely revolving around the center. The whole galaxy is twisting, warping, wobbling. One of the arms we're traveling on, the Orion Spur, slowly slopes and rises above the galactic plane like a surfer on a wave. But even the Milky Way isn't holding still. Our entire galaxy is moving, drifting, under gravity's power. A car is coming straight toward you, its engines revving. And just as it goes by, it changes pitch higher as it approaches, lower as it recedes. That's the Doppler effect. It occurs when whatever makes waves, such as sound, approaches or recedes from you. When approaching, the waves pack together. When it recedes, they become stretched out. Light behaves in the same way. When a star or galaxy is approaching us, its light waves become compressed, shifted slightly to the blue side of the spectrum. We refer to that as blue shift. If it's going away, the light becomes stretched. It moves to the red side. That's red shift. During the 1910s and 1920s, scientists began employing this trick to quantify the movement of stars and galaxies. One of them was Edwin Hubble, and what he discovered was astonishing. Most of the galaxies he looked at weren't staying put. They were moving away from us. And the further away a galaxy was, the more it was moving away. Some were zooming off at hundreds of kilometers, others thousands. Hubble graphed this out, and with each additional galaxy, the trend continued. Further meant faster. Space itself was growing, and the galaxies were just along for the ride. It was one of the largest discoveries in the history of science. It meant the universe began. It implied all that we see around us today was once a lot closer together. It even prepared the way for the Big Bang theory. But not all galaxies are fleeing. There was one that was special, a familiar neighbor, large, spiral-shaped, the Andromeda Galaxy. In 1912, an American astronomer, Vesto Melvin Slipher, took aim at Andromeda with his telescope and recorded the spectrum of its light. Then, people were just realizing how redshift and blueshift applied to galaxies, and what Slipher observed was contrary to everything they had anticipated. Rather than being redshifted like the majority of galaxies, Andromeda's light was blueshifted, which is towards us. But at that time, that was all they could actually say. Just a direction, not the whole picture. Fast forward 100 years, technology has come a long way. We've got telescopes in space, supercomputers, and an entire network of radio dishes arrayed around the Earth. Astronomers combine data from NASA's Hubble Space Telescope with precise measurements from the Gaia mission and the VBA. By monitoring the real motion of Andromeda over decades, not only the light shift but sideways motion too, they constructed a complete 3D map of its path. And what they did confirm it. Andromeda isn't merely drifting by us. It's not going to slingshot past. It's locked in. It's on a straight collision course with the Milky Way, and we're moving toward it too. It's not merely that Andromeda's coming for us. We're both hurtling toward each other through the emptiness of intergalactic space. Presently, Andromeda is traveling at around 110 km/s in our direction. That's more than 400,000 km/h. And the Milky Way isn't standing still either. We're moving towards Andromeda at close to 300 km/s if you include the motion of our entire local group of galaxies. That is, the distance between us is shortening rapidly at around 500 km/s if you include it all. But space is vast. Truly vast. Andromeda is some 2.5 million light-years from us. That's around 24 quintillion kilometers, a number so huge it barely feels real. At that rate, even with both galaxies barreling toward each other, the closing speed isn't enough to make it happen anytime soon. So, no, not tomorrow, not next year, but in about 4 to 5 billion years, the two largest galaxies will finally meet. Now you might picture this as a galactic car crash. Stars smashing into stars, chaos and fire all around. But that is not how this is done. Galaxies contain a lot of empty space. The stars within them are incredibly distant from each other on average. The distance between stars in our region of the Milky Way is around 4 to 5 light-years. That is almost 40 trillion kilometers. Even in the denser central areas, stars remain generally separated by roughly a light-year or more. For perspective, if a star were a ping-pong ball in size, the nearest other star would be hundreds of kilometers away. So even in a head-on collision between two galaxies, stars just pass by each other without ever colliding like ships passing in the night. But it's not totally serene. A few stars would actually crash into each other, particularly in the dense central areas. And a few, particularly those on the periphery, could be sent flying completely out of the galaxies, flung into intergalactic space like cosmic castaways. But gravity does the real drama. That elusive force stretches and distorts the galaxies. It sends out long tidal tails, strings of stars tugged far from home. It tears spiral arms apart. It attracts the cores closer and closer together until the two galaxies merge at last into one bigger, more disheveled system. But the complete collision isn't instantaneous. The first passage is a speedy one, a close brush that initiates the mayhem. But the merger itself, that's prolonged. It takes roughly 1 to 2 billion years to have finally settled. It's not a collision. It's a slow, elegant gravitational ballet. And when the dance is over, something new is created. One enormous elliptical galaxy. Astronomers already named it Milometer. It won't appear to be a spiral anymore. It'll be fuffier, rounder, a giant glowing sphere of stars, gas, and dust. Our sun, if it exists, will probably end up in a new orbit. Not where it is now. Not in a tidy spiral arm. It may drift farther from the center on a course more elliptical and unpredictable than it does today. But that collision with Andromeda is only part of the story. It's not the sole path our galaxy is traveling. Because the Milky Way, together with Andromeda and countless other galaxies around us, we're all drawn not only toward one another, but toward something greater, something more unusual. But in order to get a picture of where we're going, we have to zoom really far out. First past our solar system, then past the Milky Way, then even past the cluster of galaxies we're a part of. Because galaxies don't drift alone. They congregate, they cluster, they follow gravity like water runs downhill. Let's begin small. Our Milky Way is part of a group of galaxies, a cluster of about 80 or so galaxies known as the local group. It reaches about 10 million light-years across. The Andromeda and Milky Way are the two largest galaxies in this cluster. Each is surrounded by a few smaller satellite galaxies such as the Magellanic Clouds, or M32 and M110, that orbit Andromeda. But this cluster is only a small pocket of the next size up, a galaxy cluster. Clusters are gravitationally bound groups of several galaxy clusters. The local group is just one little member of the Virgo cluster, a much larger group of more than 1,000 galaxies. The Virgo cluster is about 65 million light-years away from us, and gravitationally pulls on us. And we're not floating along beside it. Our whole local group is heading towards the center of the Virgo cluster, at a rate of approximately 600 km/s. So we've got groups within clusters, Clusters of clusters create superclusters, the biggest structures within the observable universe. They can stretch for hundreds of millions of light years and hold tens of thousands of galaxies. And ours, by the way, is the Laniakea supercluster. That's the name for this immense heaven in Hawaiian. And fitting it is. Lania is gigantic, more than 500 million light-years wide, residence to about 100,000 galaxies. It contains the Virgo cluster, the Hydra Centaurus supercluster, the Parvo Ida supercluster, and the Southern supercluster, all interconnected in a web of cosmic flows. So how do we even know all this? How do scientists figure out where galaxies are going, how fast they're moving, and what they might be heading toward? It all comes down to motion. Over the past few decades, astronomers didn't just look at where galaxies are. They mapped how galaxies move. And to do that, they required more than red shifts and blue shifts. They required peculiar velocity, the real motion of galaxies in comparison to the overall expansion of the universe. Now, this is not simple. You can't simply take a snapshot and tell how fast a galaxy is moving sideways in space. You have to use lots of methods. One of the most critical is the Tully-Fisher relation. That's where astronomers measure the brightness of a spiral galaxy compared to how quickly it spins. If you have an idea of how bright a galaxy is supposed to be and compare it to how bright it appears, you can estimate its distance. And if you know both the redshift of the galaxy and its distance, you can determine whether it's moving faster or slower than the overall Hubble expansion. That difference, that's its peculiar velocity. Motion caused by local gravitational influences, not just cosmic expansion. That's where the real insights come from. Enter the Cosmic Flows surveys. Cosmic Flows 2, and later the much more detailed Cosmic Flows 3 were massive efforts to gather motion and distance data for thousands of galaxies using things like Tully-Fisher surface brightness fluctuations and even supernova data. Scientists built a 3D map of the velocity of our cosmic neighborhood. Not only where galaxies in space are, but how they were moving. And what they discovered was startling. Galaxies weren't merely expanding outward like dots on a balloon. They were also rushing in one direction toward something we couldn't see directly, something vast. And the motion wasn't random. It was ordered, patterned, a movement that pointed toward an enigmatic region of space somewhere beyond the constellations of Centaurus and Norma, hidden from our sight behind the Milky Way's dense dust lanes. This is when the true mystery began. What are we being attracted to and why? Astronomers had observed this odd flow as far back as the 1970s. Galaxies, including our own, were not simply floating with the expanding universe. They were progressing sideways with intention at hundreds of kilometers, all moving in the same direction. But when telescopes attempted to gaze in that direction, they slammed into a wall, an area of the sky we refer to as the zone of avoidance. It's filled with stars, gas, and dust from our own Milky Way, in front of our eyes from whatever lies behind it. Nevertheless, the movement was undeniable. Scientists referred to the source of this attraction as the Great Attractor, not because they could observe it, but because they could sense its gravitational pull. Whole clusters of galaxies were leaning towards it, and we were in that same flow. Gradually, with the help of X-ray telescopes and infrared surveys, astronomers started piecing together the puzzle. They discovered enormous accumulations of mass lurking behind the Milky Way's disk. Not one object, but an area full of galaxy clusters. One of the largest was the Norma cluster, some 220 million light-years away. And that cluster, it wasn't by itself. It was part of something much larger. This area, this attractor, turned out to be sitting on the edge of something much larger, the Shapley supercluster, one of the largest known superclusters of galaxies in the local universe. That's what's pulling us. The gravitational pull of the Shapley supercluster is so powerful that it warps the trajectories of galaxies over a broad section of the universe. Although we can't view it in visible light, directly, its mass is pulling our whole supercluster towards it. We're traveling at some 600 kilometers in its direction. Now the catch is, it isn't a tidy, obvious point. We're not plummeting into the Great Attractor like a rock into a hole. We're stuck in a cosmic tug-of-war. Gravity doesn't pull, it warps space. So, While the great attractor is pulling us in, other forces in the universe are warping our path too. And one of the oddest forces warping that path is not a force. It's the dipole repeller. Let's take this in slow motion. The dipole repeller isn't something. It's not a galaxy. It's not even a thing that you can see. It's a place in space that's remarkably empty. A void in space. There's hardly any matter there. No significant galaxy clusters. No significant gravitational pull. But that emptiness, it's significant because while large objects attract galaxies towards them, enormous voids do the opposite. They allow galaxies to move away easily. Think of it this way. You're drifting in a river. On one hand, there's a waterfall drawing you in. That's the great attractor. On the other hand, just flat, still water. No current, no force. That's the dipole repeller. You're not being pushed by it. You're just not being restrained. So the waterfall wins. This is what our galaxy is trapped in, a sort of gravitational current. And astronomers began to observe this more clearly in 2017, when they employed Cosmic Flow's 3 data and 3D motion maps of more than 18,000 galaxies. What they observed wasn't only a pull in a single direction. It was a dipole pattern. Galaxies like ours were streaming, flowing away from repeller and towards great attractor. But even this is not the end of the cosmic motion. When you zoom out far enough beyond the clusters, the superclusters, beyond the filaments and voids, a new pattern emerges, a deeper current, one that runs across the whole observable universe. All the major strands of the cosmic web, they're not static. They're drifting somewhere. We've traced the Earth as it rotates and orbits thus far. We've observed the sun float around the galaxy like a leaf on a stream. Then we pulled back and realized that even the Milky Way itself is in motion, part of a gigantic cosmic flow towards something we can't even see. It's already crazy to consider that we're on a moving rock that's part of a moving system that's within a moving galaxy. Now it's time to go bigger still. Now it's time to ask the ultimate question. Where is everything in the universe headed? Not only Earth, not only our galaxy, everything. Where does the universe end? To figure that out, we need to discuss something peculiar. Something that does not shine or light up. Something that behaves like it is the puppeteer pulling the strings from the shadows. Something so bizarre that science was shook to its foundations when we found out about it. The tale begins, ironically enough, with the end of the universe, or at least attempting to forecast it. 2 groups of scientists in the 1990s, one directed by Saul Perlmutter, the other by Brian Schmidt and Adam Ree, were researching exploding Type 1a supernovae. These explosions are extremely bright, and they all blow up in approximately the same fashion. That makes them ideal as cosmic mile markers. If you know how much light a supernova must emit, and it emits less than you'd expect, you know it's more distant. The objective was to find the rate at which the universe was decelerating. You heard that correctly, decelerating, because the thinking at the time was that, after the Big Bang, the universe began expanding and gravity being attractive was slowly bringing everything back. But that wasn't what the data indicated. When they measured the supernova, something didn't compute. The galaxies weren't just distant, they were too distant. The light was too redshifted, which meant the galaxies weren't just receding, they were accelerating. The universe wasn't decelerating, it was accelerating. Now picture being a physicist, and all of a sudden discovering that all of the assumptions about the fate of the universe is incorrect. That's what occurred during 1998. And rather than dismiss it, the teams double-checked everything. But the findings continued to deliver the same message. Something intangible, something strong is accelerating the expansion of the universe at increasing speeds. They termed it dark energy. We have no idea what dark energy consists of. We don't even know if it exists. But we do know that it is real and it dominates the universe. Roughly 70% of all the energy and matter that is out there exists as dark energy. To put how strange that is into perspective, imagine this. All the things you have ever seen, touched, tasted, or heard in your whole life, all the stars, all the planets, every atom, constitutes less than 5% of the universe. And another 25% is dark matter, which ties galaxies together with its gravity. And then the remainder, the largest portion of the cosmic pie, is this force pushing the universe apart in silence. So what might it be? This is where things get complicated. Physicists have a few theories. The most simple concept is that dark energy is simply the vacuum energy of space. That even when space appears to be empty, it actually isn't empty. It's seething with quantum fluctuations, random little bursts of energy popping in and out of existence. Now let's get to the exciting bit. When you work out the math, quantum theory actually predicts that empty space must contain energy. That's not the bizarre bit. The crazy part is how much. The expectation is that the vacuum energy must be 10 to power 120 greater than what we actually see. That is, quantum theory overestimates the true value of dark energy by an amount so large it's the largest discrepancy between theory and measurement ever seen in physics. This is like attempting to weigh a feather, and your calculator says it weighs more than the entire Earth. Yes, something's off. And here's the problem. This vacuum energy, the energy of empty space, isn't just sitting there quietly. According to Einstein's equations, energy and pressure shape the fabric of space-time, which means if space does have energy, then it affects how the universe expands. That's where dark energy comes in. We've observed that the universe is expanding faster and faster. So what's causing that acceleration must be baked into the very structure of space itself. And that's where scientists started thinking maybe the vacuum energy is what's powering this expansion. Perhaps dark energy is simply the energy of space that's empty. But if that's the case, then quantum theory's prediction will be the same as what we see. And it absolutely isn't. It's not slightly off, it's catastrophically off. So either our theory is faulty or we've got a massive chunk of the puzzle missing. Now let's think about this. Suppose space were like a huge loaf of raisin bread. Galaxies are sort of like raisins that get baked into the dough. When the bread cooks, it gets bigger, and the raisins pull away from one another. That's the expanding universe. But now suppose that halfway through cooking, something heat way up. The dough doesn't simply rise, it begins inflating quicker and quicker. That little bit of extra, that's dark energy. And the larger the bread, the more rapidly it expands. Because dark energy isn't simply spread throughout space, it is space. The greater the space, the greater the dark energy. It doesn't get weaker. It doesn't get used up. That's why it's so terrifying. So now we're standing here looking at a universe that's expanding faster and faster. And the engine behind that runaway growth, dark energy. This invisible, untouchable force that doesn't clump, doesn't slow down, and somehow gets stronger the more space there is. That's already weird. But now comes the truly unsettling part. Where does this take us? Let's say dark energy keeps doing what it's doing, keeps pushing, keeps stretching space. What happens in the long run? This leads us to one of the most terrifying predictions in all of cosmology. It's called the Big Rip. Here's how it works. In our current universe, gravity is still strong enough to hold things together. Galaxies don't get torn apart. Stars still orbit their centers. Planets cling to their suns. Even though space is expanding, the forces inside galaxies are still stronger than the pull of expansion in their neighborhood. But dark energy doesn't play by those rules. It grows, it's relentless, and in some models, it doesn't just keep accelerating the universe. It speeds up the acceleration. Like imagine you're in a car going faster and faster down a hill, and then the hill steepens. That's the Big Rip scenario. At first, it's nothing you'd ever notice. Galaxy clusters would spread apart gradually. The distance between the Milky Way and Andromeda would increase too quickly for them to ever collide. But it wouldn't end there. Ultimately, the galaxies themselves would start to get pulled apart. Not simply pulled apart, but torn apart from the inside out. Gravity would lose its strength. The forces that keep stars in their orbits would weaken. Then star systems like our solar system would arrive undone. Planets thrown out of orbit. Moons lost to space. The tides that kept everything in balance gone. And it continues. As the acceleration reaches higher levels, even the Earth itself wouldn't be secure. The pressure of expansion would become so great, it would disintegrate the electromagnetic forces that bind molecules together. The crust would shatter. The atoms would disintegrate apart. Even protons, the constituent parts of matter, could be ripped as space itself extends to something any particle can survive. Just before the Big Rip, the universe would be a storm of reassembled fragments. 22 billion years from now, There'll be no galaxies, no stars, no atoms, only sheer unbound energy flashing in an ocean of nothing. That is merely an estimate based on one model. It may happen sooner, may never happen, because it all hinges on how dark energy behaves, and that we still don't fully understand. But not every theory ends in shredding. Some go the other way. There's another idea, and it starts with a question. What if the expansion of the universe doesn't go on forever? What if at some point gravity fights back? You see, early in the universe, everything was hot and dense. Space was expanding, but gravity was recoiling, attempting to slow everything down. That tug-of-war has been ongoing since the start, and for a very long time, scientists considered gravity may ultimately prevail. This is the theory of the Big Crunch. Expansion is only temporary in this take on the tale. Dark energy could one day become weaker, or perhaps it was never permanent to start with. And if so, gravity may reclaim control. Gradually, to begin with, it would begin to draw everything back together. The galaxies that once moved away from one another would start to converge. Structures would unravel. The great cosmic web would tighten. On a timescale of billions of years, the universe would contract. Temperatures would increase as everything is compressed into a smaller and smaller volume. The night sky would brighten, not because new light is being created, but because old stars collide in a shrinking universe. The fabric of space-time would curve inward like a clenched fist. In the last few seconds of all existence, the entire universe would be one hot, dense point, and then perhaps it ends, or perhaps it begins again. There's something poetic symmetry about the Big Crunch. The fact that the universe ends where it started, that the Big Bang was merely one act in a cosmic play of expansion and contraction. Bang, then crunch forever and ever. But there's something wrong with this picture. The mathematics don't add up quite so well. All of the things we've seen up to this point, galactic red shifts, the cosmic microwave background, inform us that the universe is not slowing down. It's accelerating. That would mean gravity isn't winning. Not yet, at least. So unless dark energy changes radically in the future, the Big Crunch does not appear likely. But here's the thing. We do not yet really know what dark energy is at all. It's a temporary name for something we can see but cannot describe. We know it's making the universe expand more and more rapidly, but we do not know why. If anybody ever discovers the nature of dark energy, it won't be a breakthrough. It'll be Nobel reward material. But in the meantime, we have what we can see. But there's one more option, one more destiny. Not as sensational as a rip or a crunch. It doesn't boom or crumple. It just continues on. And perhaps that is the most chilling conclusion of all. This is the Big Freeze, a universe that does not perish in violence, but in quiet. This is how it comes to pass. We've already discussed dark energy, how it propels the universe to move ever faster and faster. We've also discussed how, barring any radical change, that expansion is here to stay. Consider the universe following this trajectory. Galaxies moving further and further away from each other, never ceasing. The stars within them growing older, burning their fuel one by one. This concept, the cold, endless fade, isn't merely poetic. It's supported by some of our finest data. Andrei Lind, a physicist of Russian-American heritage who has worked on inflation theory, has given input to models that favor this type of ending. Based on recent cosmological parameters observed by such tools as the Planck satellite and large-scale surveys such as the Sloan Digital Sky Survey, the expansion rate is compatible with a cosmological constant. That is, dark energy probably remains constant over time, not growing, not shrinking, just along for the ride, slowly expanding space. If that is true, then the Big Freeze isn't just a probability. It's the most likely destiny of our universe. Now let's zoom in and trace this future step by step. We're in the present moment. Galaxies are still fairly close together. Stars are forming in places like the Orion Nebula. Planets are orbiting. Life is breathing. Black holes are consuming. And the cosmic web is still radiating energy. But time will pass, a lot of time. Give it 100 billion years. By then, the observable universe, what we can see, will contract terribly. Not because the universe itself is shrinking, but because the distance between us and far-off galaxies is growing faster than light can travel across it. Those galaxies will fall outside our cosmic horizon. We'll no longer be able to see them. They'll still be there, but eternally beyond reach, such as ships going over the horizon of an ocean without end. Eventually, even the closest galaxies will be out of sight. The Milky Way and Andromeda, long since fused by then into a single giant elliptical galaxy, will be an isolated island in an empty, dark sea. Star formation is not going to continue forever. Stars require gas, primarily hydrogen, to form. But that gas is temporary. As stars become supernova or blow off their layers, they recycle material back into the galaxy. But eventually that recycling decreases. The fuel gets used up. It's estimated that star formation in the entire universe will just cease altogether in about 1 trillion years. The stars that remain, they'll run out of their fuel over long, long timescales. Red dwarfs, small, cool, low-luminosity stars, can live for trillions of years. They'll be the final beacons of light in an otherwise dark sky. But even they will burn out eventually. Ending after that, only the remains will be left. White dwarfs, neutron stars, black holes. Then we reach what's termed the degenerate era. This is when there are no new stars, no new light. The universe consists of cold, collapsed objects, brown dwarfs and black holes that are still hungry, still eating. And time just continues. In the next 10 to the power of 40 years, that's a 1 followed by 40 zeros. These star leftovers will decay. White dwarfs will get cold until they are black dwarfs. Neutron stars may hang in there for a long time, but black holes, they have a clock. As far as Stephen Hawking is concerned, black holes are not eternal. They evaporate through something known as Hawking radiation, a quantum phenomenon which makes them lose mass over time. It's very slow. A black hole with the same mass as our Sun would take around 10 to the power of 67 years to fully disappear. Let that figure sink in. Our whole universe today is approximately 13.8 billion years old. That's peanuts compared to the scale we're dealing with. In the Big Freeze, time is stretched way beyond what we can really envision. At last, all black holes decay. One by one, they vanish in small bursts of radiation. No stars, no planets, no light. The universe is a realm of particles, electrons, positrons, perhaps some decaying protons drifting alone in an ocean of cold, expanding space. Temperature approaches absolute zero, not because there is no heat, but because there's no longer anything left to create it. No fusion, no gravity holding things together, just particles drifting over an ever-expanding void. Even the protons could not last. If proton decay is real, then all matter itself could disintegrate. Some models indicate that might occur in about 10 to the power of 36 years. So what's left? Nothing really, just a faint whisper of radiation, a glow in the background from a universe that once blazed with stars, galaxies, and life. A universe that stretched out until nothing was near enough to have anything to do with anything else, cold enough never to change. Even the idea of place loses meaning. The rules that brought everything into being still exist, written into a cold, meaningless space. But nobody is left to read them. And that will be the end of our universe. Thanks for watching.